I'm the community marketing manager here and just wanted to warmly welcome you to our space. We are Dev Bootcamp. How many of you are familiar with Dev Bootcamp currently? Cool. Awesome. So Dev Bootcamp, we're the first coding program. We're a fully immersive program. We actually just had our 5-year birthday yesterday. So we're really excited to have X.AI in the space, one of the big innovators currently in machine learning. What we do here at Dev Bootcamp, we teach full stack web development, and we want to make sure that they're, some of the big innovators that are disrupting the business space are represented. And so, really excited to have you guys in the space. If you have any questions for me about Dev Bootcamp, please find me. I'll be around the event. And just wanted to introduce one of our instructors, Sunny Israni, who will talk a little bit about some of the curriculum here and how we're related to AI, which X.AI, Ben will be speaking about. And I will introduce Ben right after this.
Hello, everybody. How are we doing tonight? Good. Come on, there's all this pizza. I want a little bit more energy, right? All right, so yeah, as Rob said, we are an 18-week camp. We take complete beginners, turn them into full stack web developers. And tonight we're going to hear some great things about machine learning. And what we teach here is, we teach a lot of foundational stuff around programming and web development, so that way you can actually leverage a lot of these machine learning technologies in a way that you connect to the internet. So as Rob said, if anyone has any questions or looking to get their feet wet around web development or programming, feel free to tap me or Rob after the program.
Thank you very much. So, introducing Ben Smith. Ben Smith is a data engineer at X.AI. At X.AI, Ben works on artificial intelligence systems that, the artificial intelligence system that trains, tests, validates, and employs machine learning models. For the past several years, he has worked at tech companies in Boston and New York. He's a self-taught engineer with a formal education in politics and philosophy. In his free time, Ben enjoys playing chess and poker and builds fantasy basketball machine learning algorithms, which is amazing. So Ben will be speaking tonight about scaling machine learning, and it's a real pleasure to have you here in the space. If we could give Ben a round of applause, please.
Everyone hear me? How's my volume?
Good.
Good? Yeah? Okay. I think I'll try without the mic. Yep, so as Rob said, my name is Ben. I am an engineer at X.AI. We build an artificial intelligent personal assistant. And I'm going to give a little intro to what we do as a company to start us off. So X.AI, artificial intelligent personal assistant that helps schedule meetings for you. So we've all probably had this pain of trying to schedule a meeting with someone, the back and forth of picking a time, picking a location, figuring out who's going to be there. It takes a lot of time. It's really annoying. What we do for you is provide an AI bot that you can CC to your email, and this artificial intelligence talks back and forth with your guests. Basically, takes away the entire pain of that process and sets up the meeting for you. So it's pretty cool technology. We work on the back end using Scala. We use machine learning to solve this problem. So if you're interested in any of those kinds of problems, you can come find us after the talk, and we can talk about careers and things we have going on at X.AI. So the goals of this talk. This is an introductory talk, but basically what I'd love for us to get at the end of this is some deeper understanding of how machine learning works. And I know there's a lot of buzzwords that go around. It can end up feeling very complicated, but at the end I think we'll have a deeper foundation of what machine learning is, the kinds of problems you can solve using machine learning, and maybe we can even, and you can talk about how we can use it in other problem spaces in the future. I'm also going to talk about how when you really want to push machine learning, the thing that you need to do is collect more data and get more features. And I'll talk exactly about what those mean. But at some point, you start reaching computational limits that my laptop or any laptop in the world can provide for you. And when you start reaching those computational limits, you start needing a distributed system, a distributed architecture for solving those problems, whether it's calculating features, training a model, whatever it is. You need some sort of distributed system to solve that. And I'm going to explain Spark specifically how it addresses this kind of problem. So 2 parts, machine learning fundamentals and scaling these models. Part 1, machine learning. Did a really good job with this slide. Okay, I think at its most basic principle, it's something like this. I don't have to hard code any rules. The model and the machine itself infers from some data set, some generalities about this data, which it can apply to data it's never seen before. And I think the example that I'm going to use is a really simple example. Let's imagine that you show up at an apartment building and you want to know the price of an apartment. And this apartment building has a very simple rule to figure out what the price of an apartment is. They've got two kinds of apartments. They've got 1,000 square foot apartments and 500 square foot apartments. And the 1,000 square foot apartment is like $2,000 a month. It's a great deal. And the 500 square foot apartment is $1,000 a month. So if you're walking around in this apartment building, you come across a new apartment, and you're trying to figure out how much it costs. Well, we just pull out the tape measure, get to work, and we can figure out the square footage and figure out the price of the apartment. No problems. Unfortunately, that's just not the way it works in the real world. So if I'm looking for an apartment, and I show up in the East Village, and I try to figure out how much does this apartment cost, I don't have a rule which just tells me, yeah, if it's X square feet, it has this many rooms, it has this many bathrooms, it's next to this subway stop, I can just figure out what the price of the apartment is. Can't do that. And so what we need to do is instead, we may have in the past looked at other apartments and figured out the price of those apartments. Someone just told us what the price was, and we know things about those previous apartments. We know things about the square footage. We know things about the number of bathrooms. And using this data, what we can do is, given a new example of an apartment we've never seen before, take a guess at what the price of that apartment is. And that's what machine learning basically is we don't have these rules, the data is just too big and too complex. And so instead what we do is we look at past examples of data and infer from it some reasoning which allows us to predict on a new example. So hope that's clear, but that is what machine learning is, and I think that gets you a long way in figuring out the kinds of problems you're trying to solve. So one warning, there will be some math and some graphs. They're not going to be that complicated. Everyone in this room is going to be able to understand them, but they're going to be there. So if you see them, use your brain, we can work together, we're going to sort this out. The second warning is I have simplified some of these problems so that I can fit them into a roughly 30-minute talk. If you want to know about the complexity of these problems, we can talk afterwards and we can organize more talks. But it won't be in this talk that we go over things like neural nets at its more sophisticated level. Instead, we're going to talk about some of the more basic principles so that when we talk about these more complicated things in the future, you have this foundation to figure out what they mean and how to work with them. So when we talk about machine learning, what we generally talk about are two different forms of machine learning. There's unsupervised machine learning, where you're working with clustering and unlabeled data sets, and I'm not going to talk about that today. Other people may talk about that, I'm not going to talk about that. I'm going to talk about supervised machine learning, where we have a labeled data set, and we have some data points that you can graph in some way that looks just like this. And our goal here is to infer a function which best represents this data. That function that you derive from that data is going to be the function that you can use at a later stage to make a prediction on unseen data. So that's the kind of class of machine learning algorithms we're going to be talking about. Okay, so I'm sure everyone has seen this at some point in time, and if you haven't, it's simple, you'll understand it. So linear regression is kind of like the most basic machine learning technique that you can use. And what are we doing here? Well, we have some data points, and we're trying to fit a line. On the x-axis here, we've got square feet in hundreds. On the y-axis, we've got how much this apartment cost in thousands. And basically, if you look at this line, maybe if I give you a new square feet in hundreds, you can make a prediction about the cost of the apartment. So simple, linear regression, try to make a prediction. So what are the components of this line? Again, we're just trying to fundamentally understand what's going on here. We've got three things we need to understand. This is some slope, which in machine learning terms we call a weight. How much does this feature matter to my algorithm? We've got a bias, which in your algebra class was y-intercept. Where does this line start inside on this graph? And we've got some x, which I call a feature here, which basically means we have a continuous array, or x in this case is continuous, but a continuous line of data points which are possible inputs to my model, possible parameters my model can take. And so in linear regression, this y, which we had in this previous slide, just becomes a function, we can call it h, which takes an x here, some parameter, and given a new input, let's say 2.47 is my x here, I make a prediction, which I would guess would be $2.67 thousand, okay? So simple, we have an algorithm, we got a model, we're making a prediction prediction here. So just like kind of the basics of how this would work in terms of machine learning. And so the real problem that we end up deriving from this is, okay, so I can just stand here and start drawing some lines that go through this data, but I have no idea if this line is any better than any other line that I could have drawn, right? Like looking at these lines, I mean, you know, this one on the middle, like maybe better than the one on the right, but it's hard to really tell. We don't have any idea just from looking at the line, figuring out which one's the best line. And so basically, what we should understand about this is that every single line that I could draw through this space is going to have some cost. And the way that we calculate this cost is by looking at the difference on the y-axis between the observed data point, and if I had given you that x-axis data value, what the prediction would have been. So for example, if we're looking here at this data point that's 4 on the x-axis, the prediction would have been 4, but the actual observed data point was 3. And so that gives us some costs that we can attribute to this model. And the way that we kind of sum up all this cost. Yeah?
Can you go back to the previous slide?
Sure.
You know, in this one, all the examples that you showed are kind of taking their values and going to the ceiling point.
Yeah.
Except one value which is going to the floor. Like, you know, the one on the extreme right-hand side top.
Yeah.
Why is that?
You mean this one right here?
No, the one, see, this is still going to the ceiling. The last one on the right side.
Yeah.
Right above observed data point.
Yeah.
Why is this going down towards the floor, whereas other ones are going towards the ceiling point?
So what I'm drawing here is the difference between some observed point and the line. So this last one, the observed data point is this purple circle, and the prediction would have been this point on the line.
And how did you derive the observed data points? You already had them.
Already have them.
Okay.
They came out of the box. Someone told me what the price of some apartment was and the square footage. So if we wanted to figure out the overall cost for some line, not just like this visualization where we have some differences between some observed data points and the actual line, there's a function that can do this for us. And there are a couple that you can choose from, but mean squared error is the classic one. And so in linear regression terms, this h of x over here is our prediction. This y is our observation. And if we sum up the difference for all of those observations, we'll get an overall cost for the line. We also end up squaring it to make sure that the sign ends up being positive. And we multiply by 1/2. I don't really want to go into that, but basically it makes taking the derivative of this function much easier. So all you should know is that we're summing up the differences in the h of x's and the y's. Okay, so I explained to you what we're trying to do. We're basically trying to find a line that best fits this data. I explained to you we've got cost. Each line has a particular cost associated with it. So then the training problem here with linear regression is let's find the line that has the smallest cost. That will be the best line that we can fit with our data set. And there are some ways of going about that, which I'm going to explain to you. So the way that I'm going to describe that we can do this using linear regression is gradient descent. Now, this is not the only way that you can do this, specifically with gradient descent, and there are plenty of ways of trying to solve this problem. But if you understand gradient descent, you understand the core mechanism that very, very sophisticated algorithms use at scale. You can use gradient descent in a neural net to minimize the cost. It's one of the effective techniques that you can use. There are other techniques as well, but if you understand it here, it can be generally applied to more sophisticated things without that much work. So what are we doing here? So on the left, we have some graph. We've already talked about what this cost function is. It's some squared sum of all of the errors. And if I calculate this cost for this function, I get a value. And what I have on the right here is what it would look like if I had a three-dimensional graph where I had two working parameters. Parameter 1 is the bias of my line, where it intercepts on that y-axis. And parameter 2 is that weight, that slope of that line. And if I calculate this on the z-axis, it might end up being some cost right about here. And you're like, why do I care about the cost on the z-axis? What does that have to do with me? Well, what you can do is, if I take all of these lines and I calculate all of their costs, and when I graph on this multi-dimensional space with bias and weight, I can actually say, if I'm getting closer to the lowest point in the depth of this three-dimensional space, where cost is representative of that depth, then I'm actually getting closer and closer to the lowest cost line. the line that is best fitting this data. And so I just have three graphs over here, A, B, and C, and I've represented on this multidimensional graph what A, B, and C may look like as we step down closer to that minimum inside of that three-dimensional space. And what we do here in gradient descent is kind of iteratively using a learning rate. A learning rate is some amount that you want to step in the direction of the lowest cost. We can go closer and closer to the line that best represents this data. And gradient descent just allows us to do that. So it's just a really useful algorithm. You can use it in linear regression, and I'm going to show how you can use it in other more complicated situations as well. How are we doing so far? I talk really fast, so if you want me to slow down, just like wave your arms sporadically. Yes?
So those lines on the left, are those just different lines of best fit? Or different to the same points?
So these lines are just possible solutions to finding the best fit line. And each one of those solutions has a cost, which I described. And that cost can be thought of as kind of like on this three-dimensional graph being represented by those A, B, and C points. So if you're actually running this algorithm, what will happen is you could like calculate the cost, adjust your weight, your slope, revisualize your graph, run the cost again, get a new cost, calculate a new weight, re-look at the slope, re-look at the graph, and you would see like this line getting closer and closer and closer to approximating the data. Okay, so linear regression, pretty simple, right? We had some line, we're trying to fit some data, not that hard. There's a second branch of problems that exist in supervised machine learning, and those problems are classification problems. So what's a classification problem? If we have linear regression on the right here being, I have some data, all the data is of like the same type, housing prices and square footage, then I'm trying to draw this best fit line. But if I have, in classification, basically what I'm trying to do is find the line that best separates my data. Because instead of trying to find the line that best fits the data, I've got maybe two different groups of things that I'm trying to predict a new instance of. So like, if I'm picking jelly beans out of a bowl, maybe there's some way of predicting whether it's going to be blue jelly bean or red jelly bean. Something like that, trying to just classify what this new example is going to be. So just an example here. We have some data. Kaggle released this data set of 30,000 shots that Kobe Bryant had ever taken. And we've got a bunch of features. So in the past, we had features that had to do with the square footage of the apartment. Now we've got two different kinds of features. We have features, the height of the defender and the distance from the basket. If it looks like this data is not real data, it isn't real data. We don't have defenders who are like a little bit over 1 centimeter tall. But what you might, this is just data that represents that, we've got some shots that we've seen. We've got some examples of where they went in. We'll call those the red dots. And we have some examples where they missed. We'll call those the blue dots. So in this case, if I give you a new example of a shot that you didn't know had gone in or not, you may be able to use these features, height of the defender, distance from the basket, to predict whether or not that shot went in. So that's the classification problem. And so here, we're still trying to draw a line. But the line we're trying to draw is slightly different. And it's the decision boundary between the two groups of data. You try to draw it so it best separates the data. You obviously can't always do that. You'll have different data points that leap across the boundary. But you can still try to draw that line that best represents what best separates the data you have given in your training set. But there's a problem here, because I can pick lots of different lines. Just like I can pick lots of different lines in linear regression when I'm trying to fit if I've got housing data and prices. And one of those problems is if you have insufficient data, you can end up drawing lines that make a lot of sense for your training set, but don't make really that much sense if you're going to generalize it to some new unseen data. And so what do I mean by that? If you look at this graph, it looks great. Awesome, we've got the most perfect decision boundary you could ever have. All of the red dots are on the bottom, all the blue dots are on the outside. But if you think about it logically, in this space over here on the bottom left, yeah, like we don't have any training examples that say that Kobe took a shot from there and made it, but he would probably make it if the defender was pretty short and the distance from the basket was very short as well. And because I have some small amount of data, I can really draw this very like sharp dividing graph between the red dots and the blue dots, but I'm overfitting in the sense that if I get some new data, this graph probably does not generalize well to that new data. And so that's a problem that you want to avoid in classification. Making sure you've got very generalizable algorithms, kind of like the bread and butter of building a classification algorithm. But we still have the same training problem. We've got some cost that's associated with this line, and our goal here is to find the line that has the minimum cost. So I already explained to you how we can do this. Gradient descent gives us a mechanism for finding the minimum cost given some cost function where we're trying to step towards that lowest depth in that three-dimensional graph, trying to find the cost that is of the smallest value. And we can do this using gradient descent, where we can iteratively update the value of these weights, figure out how much the slope should matter, how much the intercept should matter, and step with closer and closer to the minimum cost. And you can see that this line, the first line I drew, has some particular cost. It starts at like the very top left end of this three-dimensional space. But as the line gets closer to the dots, closer to separating the blue and red dots, that the actual cost goes down. And as we get even closer, the cost gets closer and closer towards the minimum. Now, what ends up happening is it's hard to actually find an algorithm that is like zero cost. It doesn't really actually make that much sense. No model is that perfect. And what you'll end up doing if you train for a very, very long time is kind of oscillate along the bottom of the cost. But you get pretty close, and if you notice your algorithm isn't making that much more progress, you can usually just stop it and end up with the function that's resulted from those weights. And so again, after we've trained this, I described to you this overfitting problem. And what you do generally to protect yourself against overfitting is you test against some set of data where you know the answers, but you didn't show them to the model during the training phase. And what that does is it confirms to you as the designer of this model that you've constructed one that can work well with new unseen data. Because you can have the best model on your training set, but if it doesn't work well in unseen data, it's not going to work in production, it's not going to work in your academic setting, it's just not going to work at all. And so you need to make sure it's valid against the test set, so we usually show it some data it's never seen to confirm to ourselves that we're constructing a valid model. So classification X.AI is essentially this problem. We have different features. We are no longer trying to classify basketball shots. We're not trying to figure out the price of houses, but we're trying to understand the intent of emails and what that email is trying to convey from one person to another person. And so what we do is we use text and we construct features based on that text. Maybe we understand the way that the words are sequenced against one another, or deconstruct like the noun, verb, and pronoun construction. Or we tokenize all of these words and like check the frequencies of their arrival with the frequency of their appearance in our entire collection of documents. So we construct features from these words, kind of in the same way that we construct features when we're trying to predict basketball shots. They're more complicated, but it's the same exact problem. We can turn it into a classification problem. We're trying to classify what this email is trying to say. So just to recap, we have some input data. In classification, what we're doing is, given some input data, we try to construct a function that minimizes the cost against our validation set. And given this function, we can go to production, and we can test this out on live data and see how this model does. And if it's a good model, then we can use it on real customers and make real decisions based on those predictions. So classification can, this is kind of like how classification works. Okay, so that was part one. Yeah.
Can you just show us like a problem that we solved on meeting scheduling? What kind of things that you guys are solving? Right? Like what kind of things are solving?
Yeah.
Maybe high level, like 4 or 5 things that you can understand.
So I want to go into. The question is, can I give an example of like a classification problem that we're trying to solve at X.AI? I think there's an interesting example of a problem that we're always dealing with. It's like word sense disambiguation. It's a long phrase. Basically what it means is it's sometimes hard to interpret what people mean in the words that they say. So for example, let's say that someone says, they send an email at 1 a.m. and they say, let's meet tomorrow for coffee. What day do they mean? Do they mean the same day? It's 1 a.m. Let's say it's 1 a.m. on Tuesday. Do they mean that Tuesday? Do they mean Wednesday? And so it's a hard problem given that people frequently do this all the time. They do. Like, you talk with friends, talk with coworkers, you probably said something like this. And if you use just like a very simple rule-based system, okay, yeah, if it's after midnight and it says 1 a.m., it says let's meet tomorrow, then if it's Tuesday, we'll set the meeting up for Wednesday. But most people, when they say that, they mean meet on Tuesday. And if you get enough training examples, enough training data about how people use this terminology, you can learn patterns in the way that people try to express themselves to predict when someone says that word, what day they actually mean. And it's just, I think it's a nice example of how if you just make rules, you fail. If you try to use generalized data patterns, you're better off at making predictions.
So this example was, I think, could be calculated easily as you have explained. I was thinking of another problem which you might have faced when you were doing the word sense disambiguation. If somebody says, "Oh my God," in their email, and you're trying to decipher the words and trying to relate if he means in a good way or a bad way, things like that. How do you go about looking at corner cases like these?
I mean, so those cases are obviously tough. You can do a whole range of things. I mean, the most out-of-the-box thing, maybe you've got some like sentiment analysis, which can tell you like what the words that you're analyzing, what the general sentiment is. But along the same patterns, if you have enough training data on these terminologies, on the way that these words are put together, you can do a pretty good job of taking guesses at when someone uses it in a new context you've never seen before what they're trying to say. So, I mean, I don't have like answers to like the specific thing, but it seems like this problem can be solved with a combination of like kind of standard out-of-the-box machine learning techniques, sentiment analysis plus some classification.
And do you also use any binary trees here in trying to figure out, examples?
We can talk about this afterwards if you're more interested. So part 2, scaling machine learning. So what I've just talked to you about is kind of like basic machine learning techniques. Hopefully you'll have an understanding of like what they're basically trying to do, minimize cost, find the best fit function for the data. And that's pretty simple, pretty trivial. We should all understand that, hopefully right by now. What I want to do is talk about the computation side of things now. And before I do that, I want to get us all on the same page with some very fundamental terminology. So 4 things here. The first thing is, what is a CPU? I'm sure like if you've worked with computers, you might know, but if you've like never worked with computers before, you probably read it on your laptop description, but you probably don't know anything more than that. Basically, it's like the driver for computational work. It issues instructions to the rest of the machine to communicate some calculations that need to be done. So it does most of the heavy lifting for your computer. The more CPUs you have, the more computation you can do. But within a CPU, you have cores. And cores are the parallelization fundamentals of any computer. And what is a core? A core is basically something that can run a thread. And a thread is a logical continuation of work, logical bit of work. So if I'm trying to do something over a list of data, I've got 1,000 items in a list. Well, cores will, if you've got multiple cores, which you can do, if I've got 1,000 numbers in a list and I want to add 2 to every single number, I can split my data, if I have 4 cores, like I have in this example, into 4 chunks, have the function run against each chunk inside of that core, and get done in a quarter of the time, versus a machine that only has 1 core and can only do 1 thing in parallel. The third thing is clock cycle. And I don't want to talk that much about this, but I find it very interesting. Basically, clock cycle is the rate at which your machine can issue instructions. So you probably all looked at computers. My roommate just bought a new computer recently, and he was like, "Oh, this machine's got 2.9 gigahertz." What that means is that machine can issue 2.9 billion instructions per second. It's a very fast machine. Obviously, you can go faster, and there are limitations to that, which I'll describe. The fourth thing I want to talk about is what's memory. Memory is this really common topic inside of computation, and there are 2 kinds generally, there are more kinds than just this. But basically, what you have is you've got disk memory, memory that's stable but not very fast to access, and you've got RAM, which is very fast to access. But if you unplug your computer, everything inside of RAM is gone. So let's remember these things. CPU, cores, CPUs for issuing instructions, cores for parallelization, clock cycle is the rate at which you can issue instructions, and memory is the stuff that stores your data. So remember this scaling model problem. Wouldn't it be really nice if we just had more data here? Let's just go to NBA.com and collect every single shot that's ever been taken in the history of professional basketball. And maybe if we have all of these shots, we'll be much better at making a prediction about Kobe Bryant's specific shots. So we just want to start collecting more data. Seems very reasonable. We just start data mining as much as we can. And the problem that ends up happening is, as I scale up the amount of data I have, I can no longer fit all of this data on a single machine. It just can't be done. Maybe you can fit every single basketball shot on a single machine, but when you're working with hundreds of millions of pieces of data, it just doesn't fit in a single machine. And if you want to do some sort of job that looks at the data, maybe that trains a model, maybe that calculates some new features, then you can't do it on a single machine, and you need another solution. This is one of Facebook's servers warehouses. It's got 27,000 machines. It's a huge amount of data that they're working with. They can't just boot up my MacBook Pro, which is a pretty good computer, and run some training job on that. They need a much bigger solution. And so at X.AI, we have basically the same problem. We're calculating features that can be very computationally expensive. And at the beginning of our life cycle of building a company, it was completely okay to run this algorithm on a single machine. But as the time catches up with you, if you're waiting a day or a couple of days or a week for a job to finish, that's just time that's just massively wasted by your research team that have to wait around for this computation to complete. And it's a problem that every single company eventually runs into if you're working with data at a particular scale. And it's one that we had to solve, and I'm going to go into the way that we solved it at X.AI. So you might think to yourself, okay, well, if it's just the limit of CPU and memory and cores, let's just build the biggest machine known to mankind. I'll just start stacking CPU and cores on top of each other. I'll stick in memory sticks here and there. I'll increase the clock rate so it's doing 6 billion actions per second, and boom, we'll be good to go. We don't need anything else. Problem solved. And this is an image of a machine that's got 32 cores. The image isn't coming up great, but you can trust me, it's there. And so unfortunately, there are some limitations to this solution. You just can't keep doing this. You just can't infinitely scale your single machine. And so the biggest limitation is actually heat. And at some point, if I just keep ramping up the clock rate to issue more and more instructions, each individual action releases some heat. Eventually, my machine just overheats and explodes. So I can't just keep doing that. The other thing is, as I scale my machine, it takes more and more power. And this is a graph that shows as clock speed goes up, the way that power consumption exponentially starts to increase for that individual machine. The third thing is that it just becomes really damn hard to build a machine with no mistakes if you're trying to construct one that has tons of CPU and tons of cores. It's actually much easier to construct machines that are smaller dimensions, and you make fewer mistakes as a result of that, which is good if you're trying to build a machine that can work in a network of machines, because it's usually very bad if machines just fail out of your system. And finally, it just is more expensive. And so you're trying to reduce cost often as a company when you're constructing these solutions. And so the more expensive machines are, the more cost it's going to impact on your company. So there's a second solution, which eventually everyone gets to, which is, okay, so I can't have it run on a single machine. Does not work. Instead, I need to distribute this job in some fashion. And so we take some data, some input data, and given some coordination, I can distribute the job to a bunch of worker nodes that can do that job for me in a way that the single machine could not. And and I'll explain how that solution works and why it's a complicated solution but an effective one. So there are a couple challenges if we have a distributed system. And so the first challenge I want to talk about is coordination. And you can imagine that, let's imagine we have all this data in these trash can-like data stores over here. It would be a bummer if I started worker 1 on some slice of data, and then worker 2 was like, I need a new job, and it took the same data. Because then we get none of the advantages of having the ability to parallelize work amongst multiple machines, because they all end up redoing work that another machine has already done. The second is multi-stage sequencing. So let's imagine that I have 2 steps that I need to do in my data. Step A needs to happen first, and then step B operates on the result of step A. Well, if I'm doing some work and step A is completed, I want to notify like another set of machines that they can start working step B. But if step A hasn't completed yet, I don't want some machines to start doing step B on that data until we've finished step A. The third challenge is, okay, well, some of this data requires some of the operations require common memory objects and commands, common functions to operate on that data. And you need some singular way of, given the kind of core components of your code, distributing those common objects to all of the nodes within your cluster. And I'll explain how some solutions go about handling that. The second challenge is performance, and there are 3 components to this. Basically, if I have this, the first one is if I have this driver node, the thing that kind of organizes amongst all these nodes in the cluster, I want to minimize the drag and demand on that driver node. And that's for a couple reasons. The first is because that driver node is probably one of the most important components of your system. It coordinates with every single node, and if it goes down, it's going to be a pain in the butt to recover the knowledge the driver had. Now, if you've got a fault-tolerant system, maybe one of the nodes boots up as the driver, but on average, you don't want that driver node going down, so you prefer to minimize the demand on the driver. The second is network calls. And it can be very easy if you're working in a system, like you're working in AWS, and it boots up 3 machines for you, and you're taking a look at those machines, to think, oh, these machines are really close to each other. And I can send data from machine A to machine B, no problem. But in reality, you hope they are, but you've got no idea. That if you're using multiple areas of the country for your data center, I mean, data could be literally transferring from across the country to different machines. So you want to make sure that you minimize those network calls, because it can take a long time for the data to transfer, and it's much slower than actually just doing work on the job that you're trying to accomplish. The third thing is you want to maximize the worker memory and CPU capability. So all of these machines that you're using within your network, they also come along with some amount of memory and some amount of CPU. So if you're trying to do a distributed job, what you're trying to do is get the most out of those machines. Use all of the cores they have available. Use all of the memory that you can freely use as an application to store up some data and keep in memory some amount of your computation. So those are the challenges that kind of distributed systems propose. There are lots of other challenges that are complicated as well, but these are the 2 that I want to highlight for this talk. So the solution that X.AI that we didn't figure out but we started implementing and has worked out quite nicely is using something called Spark, which is a distributed computing engine. And what it allows you to do is it allows you to write code as if I'm executing code on a single machine. But in reality, you're using distributed data structures and distributed code to the point where you can execute this on a cluster. And you can see that this graph of a driver program and some worker nodes maps really nicely to what distributed work would look like kind of in a generalized sense. I'm going to go through some of these components and show how they solve this problem for us. So I explained to you how there's a problem with data limitations. I can't fit on a single machine all of the data. So how do I run computations if I can't serialize all of the data onto a single machine? Well, what we do is, in Spark, there is some central location where your data lives, or a distributed location where your data lives. And that data store probably has a way of splitting up the data into segments. Either just by like some ID range. We use MongoDB, and MongoDB has each document in Mongo has a particular object ID, which it keeps in an index for you. And so what you end up doing is, instead of actually having all of the data brought onto the driver machine, that data then sent out over the wire to each one of the nodes, is you say, okay, I've got this data, starts at point 1, finishes at point 40. I'm going to break it up into, let's say, 4 chunks, so that I've got 4 nodes that can all do that work simultaneously. And all I have to tell the driver is, yeah, ID 1 is here, ID 10 is here, and ship this to the node. And the node, when it wants to start doing work, goes to the database, looks up that data, and begins running some computational tasks against that chunk of data. But notice, nowhere in this process did all that data need to exist in a single place. All you needed to do is start with the start and end ID of the particular chunk that you're working on, and you can get away with never having the data live in memory on a single machine. So cool, we got around the distributed data problem where if you just scale up infinitely your data, eventually you can't fit it in a single place. The second thing is this performance problem. How do we make this job run really damn fast? And there are three things that Spark does for you to make this happen in an effective way. So the first thing it does is, if you're going to send something to a worker node, let's say that all worker nodes need to know that x equals 5, okay? And it needs to know x equals 5 for every single task that it executes on. Well, I don't want to send it per task, because if I just send it the first time and it remembered it, then it could use it on all subsequent times. And so what Spark does for you is it caches on the worker important and more important than x equals 5 memory objects that it can use in subsequent computations. So you get the advantage of not duplicating that network traffic. The second is Spark is very fast. And to understand this, you should know that most of the predecessors to Spark used disk-based memory. So the worker nodes would save and read things from disk. And that was good to some degree, because that meant that if your machine went down and it came back online, it could remember what it had been working on and restart that task at that particular point. Cool. But at the same time, reading from disk is really slow. And reading from in-memory RAM or reading from RAM is just much faster. And what Spark realized was, or the people who worked on Spark realized, is, okay, if we just keep everything in memory, sure, if this node goes down, that's a bummer, because I lose some work. But it's actually much faster to just actually have that, to have the read and write capability of going to RAM than it is to going to disk, than the cost of rebooting machine. And just like thinking about that calculation, the trade-off between losing machine and rebooting it, and the read-write speed from disk and RAM, shows that you want to keep things mostly in memory, and you get much faster applications at the other side. The third thing is CPU. You can harness all the worker cores. So basically, the executor launches on this worker and looks up what number of cores are available on this machine, and if it has some job that can be parallelized across this machine, it starts running computations on all of those cores. And so what you get is basically a pool of cores. All of these machines, if they offer 10 cores and you've got 5 machines, now you know you've got 50 cores available at any given time to run a job. And that's just way more power than a single machine probably can offer you. And so through this, you can get a much faster application running at scale, which doesn't duplicate data, which uses as much efficiency and memory as it can.
I just had a question.
Yeah.
Previously, when we're talking about Spark, is the data coming housed from somewhere else? Like, I used to, is it from a server, or is it contained within Spark?
So you can do it lots of different ways, but when I'm talking about this particular job, you'll probably have your own data storage solution, whether it's Parquet, Mongo, SQL, CSV file, text file.
Okay, so
it's on some server using some particular data storage solution.
Okay, so Mongo.
Yeah, and then Spark is the engine, which, given that data, can do some work for you. There are things like Spark SQL, which kind of blur the boundary between database and computation engine, but for the large part, it's kept separately. So just to recap, we talked about the problem of distributed computing and how at some point it becomes a really important part of your system to run some computation at scale. And when you start reaching those problems or encountering them, that you get more challenges. Challenges of network, challenges of memory usage, challenges of getting the max out of your CPU and your cores. And how Spark in particular is a very effective strategy at tackling that problem. This is just a random table that I found interesting. Hadoop, which was Spark's kind of predecessor, working on roughly similar amounts of data, just much slower than Spark at doing effectively the same job. And that's because it's really good at working with in-memory objects and very fast when it does that kind of work. Yes? Sorry?
What is the cluster disk throughput?
Cluster disk throughput. I would guess, and I haven't looked at this too closely, is that the disk throughput is like that writing to disk and reading from disk operation that I described to you. And so Hadoop, which is much more concerned with writing and reading from disk so you can preserve data in the event the machine turns off, is going to have much higher disk throughput than Spark, which is using almost everything in memory and reading and writing from memory.
Is it because of the redundancy of code?
The redundancy? Yeah. I mean, that's kind of the point of writing to disk, is you have like failover in case the application goes down.
So what if the application goes down in Spark? Is there the data redundancy built in?
So I think there is some like data redundancy built in. You'll probably end up rerunning the computation on that data. But what the Spark people figured out, and I think which makes a lot of sense, is that in the event the machine goes down and you have to like add another machine to your network, that process of like registering a new machine with the Spark driver is faster than the process of having to read and write from disk every single time you want to execute against a new task. What's up?
So Spark is just one of the example of distributed computing.
Yeah, exactly.
So can you tell us, like, at a high level, what like in the world are there like 4 or 5 ways of distributing computing, and Spark falls in which category? And the second follow-up question is that distributing computing needs to be tailor-made for a specific kind of problem to be solved?
Okay, so question 1, is Spark like, are there other ways of doing distributed computing? Are there other mechanisms of doing it? And yes, there are other frameworks which allow you to do distributed computing. There's Spark, there's Hadoop, there's Storm. You can get a lot of things out of Kafka, but what I was focusing was on Spark, but there are plenty of other ways. You can do some research into which one makes the most sense for your business needs. They'll probably, I mean, Spark it just happens to be the fastest that we have around today, but depending on what you're trying to do, another solution might be better. The second question you asked was about, do you have to make it tailor-made, Spark tailor-made for the kind of problem that you're trying to solve? And the answer is, you're going to have to write some code that accesses the data, applies some transformation, and gets some result out the other end. But the framework for distributing that work is generalizable across problems. So you don't get away with not writing any code. Like if I want to go over a list or a bunch of documents and I want to analyze the document, let's say I want to turn every single document into a list of tokens, a list of individual words, instead of just having it be one body of text or one long string, then yeah, I'm going to have to write some code that does that for me. But the process of breaking up that problem into distributed components, so chunking up documents and sending them over in the form of a task, is a generalizable solution, which is a part of like the distributed computing problem. So yeah, Spark does something for you, but not everything.
What I meant was like the whole framework itself, the choice of framework is dependent on the choice of the type of problem you're solving. That was my question.
I'm saying that
like Google
yes,
Maps, right? Google Maps might be using a framework A.
Yeah.
Versus there's one project called Aadhaar card. Like it is done in India. It is for the social security number digitization project actually. So they also do the similar kind of distributed computing. So those two are very different.
Yeah.
So do the choice of framework depends?
I would say it does depend. Yeah, it does depend on your business needs. But in general, most business needs kind of align along similar principles, which is fast is better, and Spark is the fastest. So that's what I usually think. Gonna quickly recap here, and then I'll open up the floor to questions. So takeaways from this talk. We learned that machine learning is a problem of finding kind of best fit lines given some data set. Get a function which best represents this data. And that to improve this function, to really get the max out of this function, we need to start pushing the limits of data and pushing the features that we can calculate. And as we do that, we run into some computing limits. How, the turnaround time for my job can't be on the order of days. I can't fit all of this data and all of this work on a single machine. And so there are distributed frameworks. Spark is a very good example of one, which solve this problem for you and make your processing times faster, make your computation time faster and really lowers the cost for a business overall because you're doing things at a much faster speed. So, open the floor to questions.
We have time for about 2 because Jeff will also be giving a talk as well.
Okay, sorry. You guys ask questions, so I'm going to ask.
So I guess if I understand the lecture correctly, machine learning, like fundamentally, it's about ordinary least squared regression to massive data sets.
So, I mean, regression is one technique, but I mean, it's a very common technique. I think the point of the machine learning is to say that machine learning is about deriving a function.
Right, with the least cost.
The least cost. And that's just pretty much true universally, no matter what you're doing.
Okay.
One more question? Okay. I'll talk to you afterwards. Go.
I just like the question on sampling. Obviously, it looks like more data the better, but do you also consider like sampling because do you want to learn it on the whole data set, or do you want to like bring down the sample size to obviously make the process faster and sort of focusing on the computation power of using the whole data set?
Yeah. So usually when you're trying to beta test a model, you might just train it on a quarter or even less of the data just to get something out faster. And they'll still split. So if I have, if I split it into a quarter, I'll probably still further split it into some data which I can use as validation to confirm that model is a valid model. And then if I run this validation technique and the model looks good, I'll test it on some live data in production or some staging situation. And then if it looks really good, okay, I will train like 4 days, invest all this time to really getting this model as good as it can get. But yeah, it's a common technique to start with smaller data first, just to kind of get the sense of the model, so you don't waste all this time during training and just to find out that it's garbage. Well, thank you very much.
Thank you, Ben. Thank you, Ben, for that very insightful expertise on machine learning. Really interesting. Love to hear X.AI's approach to it, so thank you for your time. Next up, we have Jeff Smith, who's the co-founder of John Dunn. For the past decade, he has been working on data science application in various startups in New York, San Francisco, and Hong Kong. He's a frequent speaker and blogger and the author of Reactive Machine Learning System, and an upcoming book from Manning on how to build real-world machine